Hello and welcome to this video lesson on chemical formulas. Specification reference 3.1.2.4. Let's have a look now at what we're going to do with our learning objectives. So firstly, we want to, by the end of the video lesson, we want to know that the empirical formula is the simplest whole number ratio of atoms of each element in a compound. So it's the simplest whole number ratio. That's the empirical formula, and the formula that you're more familiar with is the molecular formula, and we probably already know that the molecular formula is the actual number of atoms of each element in a compound. So once we know those two, we want to be able to calculate a molecular formula from the empirical formula, but you will need the relative molecular mass. So we're going to look at a couple of examples of how to do that. And lastly, we want to also be able to calculate empirical formulas from data. The data would give you percentage by mass or composition by mass. Calculate the empirical formulas from such data. Okay, let's crack on. So firstly, let's get our heads around empirical formulas. We'll start off with a molecule here. We've got a molecule of butane, and already from GCSE you will be able to work out the molecular formula. You just count the number of carbon atoms, and you count the number of hydrogen atoms, and you count 4 carbon atoms, and you've got hydrogens 4, 8, 10, and that would be your molecular formula. That's the molecular formula, but what's the empirical formula? Well, the empirical formula, as per the definition in the learning objective, is the simplest whole number ratio. Okay, so we could take this molecular formula and half each of the numbers of atoms, so you could get C2H5. You've got the same ratio, 4 to 10 is the same as 2 to 5, but it's slightly simpler. So that's good, it's simpler and it's a whole number and it's the same ratio, right? But is it the simplest? Could we perhaps go from C2H5 to C1H2.5? It's the same ratio. But it's not whole numbers. You can't go to 2.5, so we're going to give that big cross out. And so this is our empirical formula. That's our empirical formula. So what essentially in the last slide we did was we calculated the empirical formula from a displayed formula, which was very similar to the molecular formula. The displayed formula just being what the molecular formula looks like with a few bonds there. Okay, if instead we wanted to calculate the molecular formula from the empirical formula, this is what we would do. And you need the relative molecular mass. Okay, the first step would be to find the empirical mass. So you know relative molecular mass is just the sum of all the atoms in a molecule or formula unit. Well, empirical mass is very similar, except you use the empirical formula instead of the molecular formula. So that would be the first step. Then we would compare the empirical mass to the relative molecular mass. And that will become clear why we do that when we do an example. And then you would multiply the empirical formula by that number, the number that you get from step 2, to find the molecular formula. And then we will have done what we've set out to do in the title. Okay, the easiest way is to look at an example. So we have an example here. A molecule has an empirical formula of C4H3O2. But that, of course, doesn't tell us much about that molecule. It just tells us the ratio of the atoms in that compound. And it has a relative molecular mass of 166. Relative molecular mass of 166. So we want to work out its molecular formula. All right, so to save flipping back, let's just remind ourselves of our little three-step process. The first of which is to find the empirical mass. Okay, so let's write down our empirical formula. C4 H3 O2, and in the same way as we find a relative molecular mass from a molecular formula, we're going to find an empirical mass from this empirical formula. Okay, so the mass of these 4 carbon atoms is going to be 4 times the relative atomic mass of carbon, which is 12, and we've got 3 hydrogen atoms in this compound, or in this unit, and they each have a relative atomic mass of 1, and oxygen, of course, there's 2 of them, and they have the relative atomic mass of 16. Okay, so if you add those 3 up, we get 83. They all add up to 83.0. So now we have the empirical mass. And the next step is to divide the molecular mass by the empirical mass. So we've got the molecular mass 166. So 166 divided by the molecular mass 83. And you can see that's usually going to be, it's pretty much always going to be a whole number. And so you can quickly see that 166 over 83 is 2. Okay, so what that tells us, because this is about the molecule, and this is just the ratio of atoms. Yeah, so you can quickly see that there's going to be 2 units of the empirical formula in the molecular formula. That's what that's telling you. I'll just write that down for you. It's going to be 2 units of the empirical formula in the molecular formula. Okay, so that's step number 2 done. So what we can then do to get our answer is to multiply the empirical formula. So I'll write it down again for us in some nice space. So our empirical formula was C4H3O2, and if we multiply that by the ratio we've just worked out, 2, then we get the molecular formula. So when we say multiply by 2, we mean multiply each of the components by 2. So carbon goes from 4 to 8, hydrogen goes from 3 to 6, and oxygen goes from 2 to 4. And so this then is your molecular formula. Oops, extra little stroke there. Okay, so step number 3 done as well. And that's your answer. So we'll have another example just to make that extra clear. Okay, this time we've got glucose and its empirical formula is CH2O. But kindly we've been given its relative molecular mass of 180 and we're told to find its molecular formula. Okay, so let's remind ourselves of the steps. There they are. So firstly we've got to find the empirical mass. So to do that we'll write out our empirical formula, CH2O. So carbon is 1 times 12, hydrogen is going to be 2 times 1, and oxygen is going to be 1 times 16. for completeness. So 12 plus 2 is 14, plus 16 is 30. So our empirical mass, let's write it down like this instead. What did I say? 40. 30 rather, wasn't it? Okay, so the empirical mass is 30, and that's step number 1 done. Step number 2 is to divide the relative molecular mass by the empirical mass to give us the number of empirical formulas in the molecular formula so we're given the 180 as our relative molecular mass. We're going to divide that by the empirical mass that we've just worked out, and 18 over 3 is 6. So there are 6 empirical formulas in the molecular formula. So then step number 3, we can write out our empirical formula, CH2O. We're going to multiply that by 6, so you get C6H12O6, which you will probably recognize as the molecular formula of glucose. And that's steps 2 and 3 done as well. So there we have the answer. So halfway through the lesson, let's just check which of the learning objectives we've covered off. Well, when we looked at that displayed formula of butane, we worked out the empirical formula of butane, and we also looked at the molecular formula too. So that was the first 2 learning objectives. And just now we've calculated a molecular formula from an empirical formula twice for 2 different examples. So we've done this one too. So that means we can move on to calculating empirical formulas from data giving percentage by mass. So let's do that now. Calculating empirical formulas from percentages of the different elements. So what that would mean is, let's say you had a compound and you said it was 50% carbon and 50% oxygen. Work out the empirical formula. That's what the statement at the top is telling us to do. And the implication is that it's 50% by mass. So the question will usually say that, percent by mass, but if it doesn't, then that's the implication, rather than by moles. Okay, so let's go through the several step process. So the first thing, because we're dealing with percentages, first thing we can do is assume that we've got 100 grams of the compound. So then 1% is 1 gram. That makes the numbers very easy. And once we've done that, then you work out how many moles of each element there would be in 100 grams of the compound that we're dealing with. And we know the equation to work out moles from mass, so that's not going to be a problem. Then we're going to divide each number of moles by the smallest number of moles in step 2, because what step 2 is going to give us is it's going to give us a molar ratio of the atoms in a compound, but it's not going to be a nice clean integer, right? So to make it into a nice clean integer like C1H2, for example, then we're going to have to go through step 3, which is just taking the smallest number of moles and dividing all of the molar ratios, all of the molar amounts by that amount. So that would give us a molar ratio. And we just apply that molar ratio to the formula, and that gives us the empirical formula. Okay, so a 4-step process. I think it'll become clearer once we've had a look at an example or 2. So let's do so. Okay, so here's our worked example. Let's read it carefully. A compound is found to have percentage composition 56.5% potassium, 8.70% carbon, and 34.8% oxygen by mass. We're to calculate its empirical formula. Okay, so let's do it. First of all, let's get our process up. This is the process we studied in the previous slide. So we're going to assume that we've got 100 grams of the compound to make the percentages easy. So we're going to do that, and then we're going to work out the moles of each element. Okay, so let's first consider potassium. And if we have 100 grams of compound, we're going to have 56.5 grams. 56.5 grams of potassium, and we're also going to have moles equal to the mass divided by the AR of potassium. So our mass is 56.5 and our AR of potassium is 39.1, and when we put that into calculators, that comes out at 1.45 moles. So there's potassium. And next, let's do carbon. Our moles of carbon, also mass over AR. And if we've got 8.7% in 100 grams, we're going to have 8.70 grams. So 8.70 divided by the AR of carbon, which is 12.0. And plug that into our calculators, we're going to get 0.725. 0.725 moles of carbon. And for oxygen, do the same. Our moles of oxygen is going to be 34.8 grams divided by our 16.0 AR of oxygen, and that comes out at 2.18 moles of oxygen. Okay, so what you could do is you could write your empirical formula now if you wanted. Well, a sort of version of an empirical formula. You could put potassium 1.45, carbon 0.725, and oxygen 2.18. You could do that, but of course these are not tidy whole integers, and so we won't leave it like that. Instead, what we will do, so if we've done this step and we've done this step, we're going to do step 3 to simplify this. So we're going to divide each number of moles, that's the 1.45, the 0.725 and the 2.18, divide each of those by the smallest number of moles. So the smallest number of moles is this 0.725. Okay, and you'll quickly see why we do that. So if we divided this by 0.725, yeah, that's going to come out at 1. That's why we choose the smallest one. But to keep the molar ratios all the same, we have to divide all 3 molar amounts by the same number. So we divide that by 0.725, and we divide the oxygen by 0.725 as well. So then that becomes potassium comes out at 2. Carbon, of course, comes out at 1, and oxygen comes out at 3. So that is our empirical formula, just like that. Done those 2 steps in one go. Okay, so that's the answer there. Let's have another go just to make sure you're all happy with it. Here's another worked example. This time we're not given all of the elements, masses, or percentages rather. Okay, so let's read the question. An oxide of nitrogen contains 26% by mass of nitrogen. Calculate its empirical formula. Okay, let's put our steps down here. So there we have our process again, and now we're just going to work through it. So it's an oxide of nitrogen, not oxides. There's no S on there, so it's one compound, and in that compound there is just nitrogen and oxygen. So let's start with nitrogen first. We're assuming that we've got 100 grams, and so in that case we have 26.0 grams of nitrogen, and so then moles of nitrogen is going to be, I'll write out the equation for you just to remind you again. Moles equals mass over, in this case, AR, because it's an element, and our mass is 26, and our AR for nitrogen is 14. Get that off your periodic table, and so that gives us 1.86 moles. 1.86 moles of nitrogen. Now, as far as oxygen is concerned, then given that we've got 100 grams in total, 26 of which are nitrogen, then the remainder is oxygen. So 100 take 26 is going to be 74 grams. 74.0 grams is our mass of oxygen, but equations always use moles. So our moles of oxygen are going to be mass over AR again. So the mass in this case is 74 grams of oxygen, and the AR of oxygen is 16. And that comes out at 4.63. 4.63 moles of oxygen and 1.86 moles of nitrogen. So we could write our odd empirical equation down. So oxygen is, although they're both non-metals, in this case oxygen is going to be the most electronegative, and so we're going to write that on the right hand side. So it's going to be nitrogen 1.86, oxygen 4.63, which is the smallest. So let's just tick off our process. We've made that assumption of 100 grams. We've worked out the moles of each, and we're now doing step number 3. We're going to divide each of these molar amounts by the smallest number. Smallest number is 1.86. So let's do that. 1.86 and 1.86. So we keep the ratio the same. So our odd empirical formula becomes nitrogen is obviously going to be 1.86 over 1.86 is 1, and oxygen, if we put 4.63 divided by 1.86, we're going to get 2.5. Okay, so it's still a little bit odd. 2.5. So that also is not a whole integer. So we can improve that again and just double both. So we would have N2O5, and that would be our empirical formula, N2O5. Okay, so these two examples that we've just done are fairly simple examples, and that's to just get us used to using that 4-step process to work out the empirical formula. But if you were to get an exam question on empirical formulas, it's more likely that the exam question will describe an experiment, and from the results of that experiment then you have to get the empirical formula. So we'll have a look at a couple of questions that might have been exam questions. So here's our exam question, and let's read it carefully. When a hydrocarbon is burnt in excess oxygen, 4.40 grams of carbon dioxide and 1.80 grams of water are made. What is the empirical formula of the hydrocarbon? Okay, so looking at that question, the first thing we have to intuit, to use an American word, is that the carbon dioxide has been produced, and where is all that carbon coming from? All the carbon is coming from the hydrocarbon. And for the water, which of course is H2O, where is all the hydrogen coming from? Well, the hydrogen is coming from the hydrocarbon as well. And of course the oxygen that's in the carbon dioxide and the oxygen that's in the water, they're coming from the air that's helping the hydrocarbon to burn. Okay, but the oxygen we're not worried about. Okay, so I'm not going to stick the 4-step process up this time because it's a slightly different process that we'll go through, but we still start with calculating the number of moles. But this time we're going to calculate the number of moles of the two products that we get. So if we start with CO2, we've got 4.40 grams of carbon dioxide. So CO2, the moles of CO2 is going to be mass over mR. We've got 4.40 grams, and the mR of carbon dioxide is going to be 12 plus 2/16, which is 44. In which case that equals 0.100. So we're sticking to 3 significant figures. So we've got 0.100 moles of carbon dioxide. And in exactly the same way, we can work out the number of moles of water. So the number of moles of water is also equal to the mass over mR. And we've got 1.80 grams of water, and the mR of water is going to be 2 plus 16 is 18. And that is also 0.100. Okay, so now we've got the basics down. We need to just have a little think about what's going on here. So, as we said when we were looking at the question, all of the hydrogen and all of the carbon comes from the hydrocarbon. And this means that we can use the number of moles of carbon dioxide and water to work out how many moles of hydrogen and how many moles of carbon were in the hydrocarbon. So first of all, let's look at the carbon dioxide. So the carbon dioxide contains, so 1 mole of carbon dioxide contains 1 mole of carbon atoms. It's a 1-to-1 ratio. So the original hydrocarbon must have contained 0.1 moles of carbon atoms as well. So the hydrocarbon contains 0.100 moles of carbon. Okay, now water is slightly different because look, we've got H2O. So 1 mole of water, 1 mole of H2O contains 2 moles of hydrogen. So the original hydrocarbon must have contained 0.2 moles of hydrogen atoms. Okay, so hydrogen contains 0.1 moles of carbon, but 0.2 moles of hydrogen. Okay, so now if we can write an odd version of the empirical formula, you would have carbon 0.100 and hydrogen 0.200, and so then we're going to divide both sides by the smaller number, which is 0.1, and that gives us C1H2, but we don't write the 1, so we're just going to write that CH2, and that's our empirical formula. And the difference really between this one and the first two was the little bit of intuition that you need to do, as well as just follow the process. First of all, you need to work out that all of the carbon is coming from the hydrocarbon, all of the hydrogen is coming from the hydrocarbon, and you also need to spot that there are 2 moles of hydrogen atoms in 1 mole of water molecules. Once you've made those intuitions, then the rest is fairly easy. Okay, let's have another go just to embed that for you. Here's a different one. We've got 2.50 grams of copper this time, and we're heating it so that it forms copper oxide, and we're forming 4.13 grams of copper oxide. So what is the empirical formula of the oxide? So first of all, let's have a little think about how we're going to do this. So let's remind ourselves that empirical formulae are just need the number of moles of each of the elements in the formula. Okay, so we've got in copper oxide, we're going to need the moles of copper, and we're going to need the moles of oxygen. That's all we're going to need, and then we're going to work out the molar ratio and make that into a nice empirical formula. Okay, so the tricky bit is the intuition here, and it's not that tricky. The moles of copper first is easy. It's going to come from 2.5 grams of copper. But how are we going to get the moles of oxygen? Well, we're given the mass of copper and we're given the mass of copper oxide. Okay, so if we look at the difference between the 2.5 of copper and the 4.13 of copper oxide, that difference is going to be the mass of oxygen. And once we have the mass of oxygen, we can work out the moles of oxygen. And once we've got the moles of oxygen, then we have everything. Okay, so that's what we're going to do. Nice to look at it at a high level first, get ourselves a little plan, and then we can work through it. Okay, so let's start off with copper. Copper is easiest. So we're going to start off with copper, and we've got 2.5 grams. So moles of copper are going to be mass, which is 2.50, divided by the relative atomic mass of copper. So that's going to be 2.5 over 63.5. So we've got 0.0394 moles. Again, we're dealing with three significant figures. So we've got 0.0394 moles of copper. So that's a good start. So let's switch to oxygen. So the moles of oxygen are going to be our mass of oxygen. So the amount of oxygen we've got is going to be the difference between the mass of copper oxide minus the mass of copper that we started with, because we have to assume that we've not lost any copper in this process. So we're going to put that in brackets, and then that's all going to be divided by the AR of oxygen. Okay, so that's going to be 0.630 divided by 16 atomic mass of oxygen, which also comes out at 0.0394. Okay, so now we've got the moles of both, and we just have to convert those moles into a molar ratio to give us our empirical formula. Okay, so let's do it the long-winded way. I think you can see what the answer is going to be already, but let's do it the long-winded way anyway. We've got copper, and we've got 0.0394, and we've got oxygen, 0.0394 as well. And we look at the smallest one. So the smallest one is both of them, 0.394. So we divide both by the smallest one, 0.394. So both of them are 1, so we get, and we don't write the ones in, and so there is our empirical formula. So, of course, that's not carbon, it's copper. So our empirical formula is copper oxide. Or we could write that, just for completeness, we could write that as copper 2 oxide, because as you'll learn later on in the course, copper can form more than one oxidation state. But there we are, that's our empirical formula. So going back to our learning objectives, we've already checked that we did this with butane, and then we looked at a couple of examples from relative molecular masses, And the last one, we've just looked at 3 or 4 examples of calculating empirical formulas from data, whether they be grams or percentages. So we've done the lot. Hope that's been clear. Any questions, put them to me in class. Thank you.